Hi there. Today we're going to look at geometric properties of an area, specifically centroids and moments of inertia. For those of you who either didn't have this previously or took it previously but forgot about it, we're going to go over this. We're going to start with some of the theory, and then we're going to talk about some of the practical applications and how we actually use it. Okay? So what is moment of inertia? Moment of inertia is the second moment of area. But before we understand moment of inertia, we have to talk about what the centroid of an area is. In engineering, we use a lot of cross sections. We do a lot of 2D work. We'll take 3D elements and we'll take cross sections and look at the 3D cross sections. So the centroid of an area is the point that defines the geometric center for the area. All right, if you have an arbitrary shape like shown here, so if we have an arbitrary shape like this, we want to know where is the centroid of that area. We were going to look at some point here in the center. It's the geometric center. But how do we find that? We're going to look at a little differential element, dA, right? And that differential element dA, dx dy, we're going to measure that from some coordinate system. So we'll measure up to the center of that element, right? And we'll measure over to the center of that element. And we'll call that, this is the x-axis and the y-axis, right? So we'll x distance and y distance. And we know, because we've done it a lot, that if we take a little square, the center of that square is at the center of that square, right? So then what we're going to want to do is we're going to sum up all of these little areas and all of their little distances. And what comes out is that the x bar, that is to say the centroidal distance, right? So that's the centroid distance, the location of that centroid, is equal to the integral over the area of x dA divided by the integral over the area of dA. We can do the same thing for y bar. We can say that y bar is the integral over the area of y dA over the integral of dA. Now, from a practical standpoint, I mean, that's a lot of fun, and we can do that. But from a practical standpoint, what that comes down to is we say that x bar is equal to the sum, right, of xa over sum of a. And in the book, they use a little tilde over that. All they're really trying to say is we take all of these little individual pieces, we sum them up. And for the same thing for y bar. Y bar is equal to the sum of ya over sum of a. A lot of times in engineering, of course, we take integration, we break it down into summations. So that if we wanted to look at the centroid, right, of a section, of a cross section. So let's say we have a beam, right, and we take a cross section of that beam, and that beam has a cross section that looks like a T. Okay, so it looks like that. We can break that into two sections, two pieces. We can have an upper piece and a lower piece. Then we have one and we have two, right? And you can do this for as many pieces as you have. Then we can say that if we'll put some dimensions on here, we'll say this is 8 inches. We'll say that this is 2 inches thick. That this one is 3 inches thick. That this distance here is 10 inches, no scale, of course. And we're going to find where y bar is. So we're going to say this is x and this is y. Measure y up here. Now, one thing we know, that the centroid always lies on an axis of symmetry. Now, if you don't have an axis of symmetry like this one, then you don't know where it is necessarily, although you can kind of eyeball it. But if you do have an axis of symmetry like this, we know it's going to be right on that axis of symmetry. So we don't need to calculate x bar. It's in the middle. Okay? But we do need to calculate y bar. So let's figure out what that is. So we'll say y bar is equal to, of course, the sum of ya over sum of a. And so that's going to be equal to the first one, where we're going to say it's the y distance the y distance is going to be 11.5, right? So that's measuring from here to here. That's 11.5. That's 10 plus 1.5, because we know it's in the middle there, right? So 11.5, this is all in inches, times the area, which is, oh, we didn't define the, oh yeah, we did. We said it's 8 inches, didn't we? So it's 8 times 3. 8 times 3. And then we have to add the next section, section 2. Well, that area is 10 times 2, and that y bar is 5. Or that y, excuse me, where the distance of the centroid is y. And then we're going to take that, and we're going to divide by the summation of the area, which of course is 3 times 8 plus 10 times 2. Okay? And we get our calculator and we run through the numbers, and we're going to find that y bar is equal to 8.55 inches. Remember, this was all in inches. This is in inches, this is in inches squared, because it's area. This comes out inches to the third, right? And so you get inches. So where is that in our picture here? Again, there's no scale here, but it's going to be up in this general vicinity, right? If the height is 10 and we're at 8.55, we're almost to the top. So remember, that's the center of the area in the y direction. And that's how you find centroids. Now, you can also do it the other way. What I mean by that is, if you have, so this is a thing here. Another thing, technical term thing, is that holes, right, are negative. Have negative area. Holes have negative area. So that means that we can also subtract holes. So if you had a circle, say you had a circle like over here, a circle with a tube, you could calculate the outer and subtract the inner, and you'd get the right answer. Now, of course, for a circle, you have 2 axes of symmetry, so you know it's at the center of the circle. You don't need to calculate either one. That's why a square, you know where the centroid is too, because I told you it always lies on the axis of symmetry, right? But holes are negative, so how could we use that in this case to help us? Well, we could, if we wanted to, we could take a block that was 8 by 13. Yeah? And then we could subtract, let me get another color here. I don't know if purple will show up, but we'll try it. We could subtract this area, and we could subtract this area. Okay? So what would that look like? We'd say y bar is equal to, again, the sum of ya over sum of a. So that's going to be equal to, well, the block, it's right again at the middle, but it's going to be half of 13. and half of 13 is 6.5. So it's 6.5 times that area, which is 13 times 8, right? But now we're going to go minus, right? We're going to go minus, and we got two of these things. So there's 2 times their distance. Well, we know this was 10 up from the bottom. We're measuring, got to measure from a consistent direction, right? So we're going to measure up from down here, from the bottom. That distance is 5 times the area of 10 times 3. And that whole thing then gets divided by the area again, 13 times 8 minus, and again we still have that 2 in there, 2 times 10 times 3. Okay? So again, we took the whole block, that's this one, and this area here, minus the 2 pieces that we're subtracting out. So this is subtracting out the area. This subtracts out the YA. And then we do the calculations, and sure enough, it comes out 8.55 inches. So same answer. Good. 2 different ways. So what have we learned so far? Centroids. It's the center of the area. Right? So let's write that down. Centroid. Here, we'll write it down on a new piece of paper. So we said a centroid is center of the area. We also said that the centroid lies on an axis of symmetry. Right? And we also said that holes are negative area. This would be centroid. There. All right, so holes are negative area. Centroid lies on the axis of symmetry. Centroid is the center of the area. Great. And we also saw that we can do things in parts, right? See that? We can take this and we can divide it up into pieces that we know the answer to, like we did here, and we can sum up those parts. Okay. What's the next thing we want to talk about real quick? We're going to talk about moments of inertia now. So we found out how to find the centroids. That was important. That's sort of step 1. Now let's figure out how to find the moment of inertia. Again, if we have that same amorphous blob, right, and we have some axis system, we have an ordinate down here, we have our dA element over here, and of course we're measuring our distance x and our distance y to that area. We can also measure the distance r, radius, to that area. Now we define the moment of inertia as the integral, if we about the x-axis, the integral of, Ix is going to be the integral of, over the area, of y squared dA. So it's the second, right, moment of inertia. The moment of inertia is the second calculation, right, where, remember before we had YA for finding centroid, now we've got y squared A. And similarly, IY is going to be x squared dA. Now here's an interesting thing. We've already talked about torsion, and we talked about polar moment of inertia, right? J as the integral of r squared dA. We didn't define it that way, but that's what it is. We just told you what the answer was. Guess what? That's equal to Ix plus Iy. Generally, for torque elements, we like circles because they're very efficient. But you could do it with any shape. If you want to find the polar moment of inertia, this is the polar, right? Moment of inertia. It's Ix plus Iy. Now we'll get to some practical applications here in a minute of how we actually use. Yes, we could do some integration, and if you go back and look at Hibbler's statics book, he will give you some funky curves, parabolic curves like that, and ask you to do some integration, or he'll give you other curves, and But we're not going to go there today. If you really need to work on that, study some unique curves, we can show you how to do that. But this is where it comes from. Okay, this is the basic. However, there's one more thing we need to talk about, and that's called the parallel axis theorem. P-A-R-A-L-L-E-L. There we go. Axis. T-H-E-O-R-E-M. There we go. Parallel axis theorem. What that says is if I have, again, my amorphous blob, and I know the moment of inertia about the centroid. Right, so if we call this just XX, I can say if I know we call it I naught or Ix, but it's the moment of inertia about the centroid. This is the centroid, right? I can move that, or Ixx. You'll see it written different ways. Ix or Ixx or I naught. But if we want to move it to another location, we want to say, well, what's the moment of inertia down here by x prime? We can do that. We can say, we can calculate it as Ix is the integral over the area of y prime, this distance, plus dy, dy squared dA. What that means in a practical application is that Ix prime, this should be a prime, sorry, is going to be equal to I naught plus AD squared. Wait a minute, what's D? D is the distance from the neutral axis, from the centroid, from the centroid to the new axis. All right? It's the distance from the centroid to the new axis. I guess I drew that wrong, didn't I? This should be D here. And Y should be... Anyway, this is... let me draw that again. We're going to want to move it... If we know this and this, this is D. This is the centroid. This is X prime, the new one. And that's D, the distance we're moving it. Now note that two important things. One, I naught is the minimum, is always the minimum. Because every time we calculate a new one, we add AD squared. Okay, so I naught's always the minimum. The other thing is you can only go to or from I naught. You can't say that, you cannot, this is no. You can't say that Ix double prime is equal to I prime, Ix prime plus AD squared prime. Nope, can't do that. Don't do that. Bad. Okay, it doesn't work. If you want to do it about a new axis, say here's x double prime. You can't go from x prime to x double prime. You have to go back to x. And you might say, well, why doesn't it work? Well, think about it. Think about it. If this is d prime, I get squared terms involved, don't I? So you got to move back to here and then from here to there. Okay, so just always go through I naught, you'll be fine. So that's wonderful, you say. What do we do with that? Well, oh, I guess I should talk about, I love to talk about nomenclature. So, let me blow this up a minute. I can zoom in on that. You may see this, and again, another way to write the same equation. You'll see here Ix, right, equal to Ix prime bar plus AD squared. In this case, what they're saying is this is the moment of inertia about the centroid. Always be careful about nomenclature, but that's what they're talking about if you see it written that way. So what does that mean for our little block that we had earlier? Remember our little block that we had earlier? Oh, gotta zoom back out. There we go. We said that this little, remember we calculated the centroid already. Let's duplicate this. We said this was 3, this was 8. This is all in inches. And this is 2, right? And this is 10. And we found that y bar was equal to 8.55. Okay, inches. Measured up from the bottom. How do we calculate I of that? Once again, we can do it in parts. Okay. This is called oh no, not that. That's product of inertia. This is called, just do it, composite areas, right? This is called composite areas. And what that means is I can take, again, 1 and 2, and I can sum them up, just like we did before, and come up with a total moment of inertia about this axis. So this is my centroid right here, right? Now, we know the centroid of this block number 1, but do we know the moment of inertia of block number 1? And the answer is yes, we do. So where do we get that? Well, once again, you go to the end pages of your book. Right here on this end page, it tells you geometric properties of area elements. Here's a rectangle. It's 1/12 BH cubed. That's the moment of inertia about the centroid of that element. Here's a triangle. It's 1/36 BH cubed. Here's a trapezoidal element. Here's a circle. Ooh, circles. A circle, right, here's the area, pi r squared. And here's the moment of inertia, 1/4 pi r to the 4th. Remember that we had polar moment of inertia of 1/2 pi r to the fourth. Well, if you take 1/4 and 1/4 and add them together, you get 1/2. All right. So this table becomes really useful for the things we're doing. You're going to want to memorize a rectangle. Why? Because, there we go. Because you're going to use it all the time. A lot. You might end up memorizing a circle too, but definitely remember a rectangle. Okay. So we know that the moment of inertia about number 1 is 1/12. The base, well, the base is 8, times the height, which is 3. But that's about an axis up here, right? Not about the centroid. We have to move it to the centroid. How far is it to the centroid? Well, this is at 11.5, and this is at 8.55, and it's squared. Oh, and now we have to I need a plus in there. There we go. And the area is 8 times 3. Oh, and this needs to be cubed. There we go. 1/12 BH cubed. 1/12 BH cubed plus AD squared. And that's going to be the new moment of inertia for number 1 about the centroid. So they get all that right? 1/12 the base times the height cubed plus, here's the area, times d squared. Okay. Then we're also going to add to that, we're going to come up with I2, also about, and move it to the centroid. So I2 is 1/12 the base, what's the base? 2 times the height, 10 cubed, right? Plus AD squared. The area is 2 times 10, and d squared is now 10. Well, it's actually 8.55, isn't it? 8.55 minus 5, because it's down in here is the centroid of that one, squared. Now, something to remember, this is always a positive term. Well, unless area is negative, right? But d squared is always positive. So it doesn't matter which order you put these in. We're just looking for the net difference between the centroid of the element that we're adding and the centroid of the total of the composite area. Okay? Let's see, did I do that right? This is 8.55 minus 5. Yep. And does this other one come out right? We said this was measured up here to 11.5 minus 8.55. Okay. So now this, yeah, that's right. When you add these two together, so I of this cross section is going to be equal to I1 plus I2, and that's equal to 646 inches to the fourth. Okay? Now, once again, we could have done this the other way. We could have taken our block and subtract out these two areas. And you will get the same answer. So I is equal to the sum of I naught plus AD squared, right? So what are those again? So with the first one, it's going to be 1/12 the base, 8 times the height, 13 cubed, right? Plus AD squared, so that's going to be 8 times 13. Remember, this is 8, and this is 13. 8 times 13 plus d squared is once again going to be 8.55 minus 6.5. 6.5 being the center of the block that we're looking at, squared. 1/12 bh cubed plus a d squared. And then we're going to add to that, or actually we're going to subtract, aren't we? Yeah, we're going to subtract 2 times these two I naughts, which is 1/12 times 3 times 10 cubed plus ad squared, 3 times 10 times 8.55 minus 5 squared. And we subtracted here because we have these are holes. So they have negative consequence, and they're taking the moment of inertia away. Anyway, when you do your arithmetic in your calculator, it comes out to 648 inches to the fourth. Let's talk about units. All right. Y bar is distance. So it's going to be in inches, or it could be or millimeters, right? Or meters, something like that. Distance. Could be in feet, although generally not. Inches and millimeters are the typical things we're going to be using. Moment of inertia, I, right, is going to be distance to the fourth. See, we have inches to the fourth. AD squared, inches squared, times distance squared. BH cubed, we should come either to inches to the fourth, or millimeters to the fourth, or of course it could be meters to the fourth. Just remember that 1 meter is equal to 1,000 millimeters. Or the other way to say that, right, 1 millimeter is equal to 0.001 meters. 10 to the minus third. So when you're calculating your moments of inertia, just be careful, even in metric, of what your moments of inertia are, right? Watch those units. No crashing into Mars. Okay, let's keep going. Next, we're going to talk about unsymmetric sections. Unsymmetric sections. Remember I said that your centroid is going to line on your symmetry. What if we don't have symmetry? What do we do? Well, we have a thing called product of inertia. Okay, product of inertia. And that's I x, y. And that's equal to x, y, dA over A. That implies that there's coupling, right? Coupling between x and y. And it means that the principal axes are not in the xy plane, are rotated from x and y. We draw these axes to be convenient for us for one reason or another. That doesn't mean that the material thinks it's convenient, right? It gets a little bit more complicated. There is a parallel axis theorem too. That says that I xy prime, right, is going to be equal to I xy bar, or not, plus a dx dy. All right, let's look at an example of how to deal with one of those. If I have a cross section that looks like this, I will draw it over here. You're going to come down 400, 1, 2, 3, 4. We'll go over 6. Well, we gotta make it 100 wide. Bonk, 1 wide. Okay. Go down 3. 1, 2, 3. Then we're going to go across 5. 1, 2, 3, 4, 5. And then we're going to go down. And we're going to go down 4. 1, 2, 3, 4. Okay, there's our cross section. All right. Well, if this actually has an axis of symmetry, doesn't it? Because if I draw a line through here, there's as much area on the top as there is on the bottom. All right, but let's go ahead and calculate. So we would just show that there is no product of inertia. That when I went through the process, I'd get 0. But what if they were different? What if this had a different thickness, or this had a different length, or then we'd have to go through this. Okay. Let's, however, look at the axis about y. Okay. Well, let's calculate some of these products of inertia. Where is the axis here? Well, we know it's going to be here. Actually, it's going to be there for both, but if we look at rectangle, we're going to label these, A, B, C. If we look at rectangle A, we're going to say that, I keep going crooked for you. There we go. Let's try that. We'll say that IXY is going to be equal to IXY prime plus A dx dy. Well, that's going to be equal to 0 because the first one is just a rectangle, plus the area 300 times 100. This is all in millimeters. Oh, I didn't define these for you. Let's see. This is 300 to here to here. And it's also 300 from here to here. These are all 100. This is all in millimeters, right? And this distance from here to here, this is, wait a minute here, let me do it this way. This is 600. Okay. And then this distance to here, let's see, this is going to be 250. And similarly, over here is 250. All right. So the area, it's 300 times 100 times dx. It's minus 250. If this is our axis system, we got to go minus 250. And then we have to multiply by the other direction up to here, which is 200. That's from here to there. Now note that you can see here we no longer have a positive number, right? We're not squaring a distance. We have two distances that we're multiplying times each other. So we got to be careful on our signs because it will make a difference. And so for that case, it comes out to negative 1.5 times 10 to the 9th millimeters to the 4th. What about B? B is going to be 0, 0, because we're about, you can see that by inspection, right? You're on this axis, you're on this side. Guess what? You're on that axis. So IXY of B is going to be 0. What about C? C is going to be equal to, we're over here now, right? And that's going to tell us that IXY, first we have to say it's going to be 0, because again it's just a rectangle, right? So it's not going to have any IXY of its own, but we do have an ADX dy to worry about. So that's equal to that area, which is 300 times 100 times 250, because we're going from here to here. But now we're going down. Uh-oh. Now we're going down. So you go down 200. So based on the axes we picked, we have a negative distance to that centroid. And that comes out to negative 1.5 times 10 to the 9th millimeters to the 4th. So now we're going to add these up to get the total product of inertia for the cross section, right? So the total IXY is going to be equal to minus 150, and that's of course times 10 to the 9th millimeters to the 4th, which of course is equal to negative 300 times 10 to the 9th millimeters to the 4th. So there is a product of inertia for that cross section. We can also look at the inclined axis for this, because the axis of what was called the principal axes, that is to say principal axes, where IXY equals 0. That's what we're looking for, is where IXY equals 0. Okay? By the way, this all comes into play when we start doing bending. What does that really mean? It means when if I put this in bending, it's not going to want to bend about these axes. It's going to want to bend about the principal axes. So you're going to get secondary bending, even if if this is x and y, right? If I put mx on here, I'm going to generate my. It wants to move to be on the principal axes. Okay. It's not too hard to calculate these. What we're going to find is that, I say not too hard. Let me zoom in on these puppies here. There we go. It's a lot easier for me just to show you this than to try to write it. But these are the equations for finding the principal axes. All right, so this is using baseline. If we want to know where the principal axes are, this here, I'm going to show you this picture first, I guess, right? That would help. Whoa, settle down. There we go. I have x and y, and I have x prime and y prime. X prime and y prime, in this case, represent the principal axes. If I'm going the other way, I need those other equations. But we don't usually go that way. We usually have ix and iy, and then we and ixy, right? And then we calculate where the principal axes are. So let's show you how to get to the other. All right? Okay. All right. We're going to say that if we have x and y, and there's some principal axes, this is x, this is y, x prime and y prime. And we just want to rotate into those axes. And so this angle is theta. Oh, sorry, I'm off the screen. There we go. We have x and y, and we're going to rotate into x prime and y prime. Okay? What we can show is that the tangent of 2 theta is equal to negative ixy over ix minus iy over 2. Now let's take a look at this. You can see right away that if we have double symmetry and ixy goes to 0, then theta goes to 0, which is what we wanted, right? So if you just had a rectangle with ixy of 0, that is the principal axis. But if you have a positive, if you have a value for ixy, then that principal axis is rotated. What if we want to know where that axis is? Well, we're going to change things up on you just a little bit. First, we're going to change our definition of our circle. We're going to draw the circle like this, where this is I, and this is ixy. Okay? And this angle is 2 theta p. Well, wait, where did theta p come from? Well, theta p is the angle to the principal axis, that's all. Theta is equal to theta p. Okay? It's again where the where IXY would be equal to 0. All right. We can define this location. This is going to come back to haunt us when we talk about Moore's circle, so you may as well learn it now. This distance is IX minus IY over 2 from here to here. And this is IXY. And this distance from here to here, right, square root of the sum of the squares, is the square root of IX minus IY, over 2 squared plus IXY squared. That's that distance from here to here. So that means that our I max or min is equal to IX plus IY over 2 plus or minus the square root of IX minus IY, that's a Y, sorry, over 2 squared plus IXY squared. Okay? So now we know how to find the angle of to the principal axes. That becomes a P, right? If we can find the angle to the principal axes, we can find the magnitude of the principal axes, max and min, and now we can calculate our moments. Again, we can use that to calculate our stresses and strains and moments. All right, so what does that mean for that little example we were just playing with, that little one with the negative 300 I? This should be, I think, we're nearing the end of our dissertation here. But determine the principal axes. Well, remember we said we had our little device looks like this, a little Z section, because it looks like a Z. And we want to find out where the principal axes are. This was X, remember, and this was Y. So we want to know what this angle is here. Okay, this is theta P. And this is going to be X prime and Y prime. Yep, I'm off the screen again. Sorry about that. Okay, here's our Z section. Here's our angle, X, Y, theta P. We said from before that IX was equal to 2.9 times 10 to the 9th millimeters to the 4th. We said IY was equal to 5.6 10 to the 9th millimeters to the 4th. And we said that IXY was equal to minus 3 times 10 to the 9th millimeters to the 4th. Oh, correction. That should be a period. Sorry. Yeah, remember, watch your units. Me too. All right. Theta. So we said that the tangent of 2 theta p was equal to minus ixy over ix minus iy over 2. Well, that's going to be equal to 3 times 10 to the 9th over 2.9, again, times 10 to the 9th minus 5.6 times 10 to the 9th. And that's going to be equal to minus 2.22. Now, note that we had a negative here and a negative here, so now it's a positive there. We're subtracting ix from iy. Iy is actually larger, so we're still going to get a negative value. And it's dimensionless, over 2, sorry. It's dimensionless because we had millimeters to the 4th divided by millimeters to the 4th. So that's good. That's good because now we can take the arctangent, right, and find that 2 theta p is equal to 114.2 degrees. That's this one. So what's this little one here? Well, it's going to be theta minus 90, right? And so we'll call it 2 theta p2, p1. This is p1. This is theta p2. And p2 is going to be equal to minus 65.8 degrees, which makes sense because we're rotating down. This is positive, right? So now we're rotating down to find theta p2. Or if we divide by 2, theta p1 is equal to 57.1 degrees, and theta p2 is equal to minus 32.9 degrees. Because 57.1 minus 90 is 32.9. Okay. Now, what are the values? So we know where the axis is. Axes are. What are the values? Well, we'd go back and we'd say that I max min is going to be equal to IXY, right? IX plus IY over 2 plus or minus the square root of IX minus IY over 2 quantity squared plus IXY squared. So we will say IX is 2.9 plus 5.6 over 2 plus or minus the square root of 2.9 minus 5.6 over 2. I should put those in there. This is all times 10 to the 9th, right? Because I got to square this. I got to square that. Plus minus 3, again, times 10 to the 9th squared. So this is all 10 to the 9th, 10 to the 9th, 10 to the 9th. Square root of the squares. And that comes out to 4.25 times 10 to the 9th plus or minus 3.29 times 10 to the 9th, which means that I max is equal to 7.54 times 10 to the 9th millimeters to the 4th, and I min is equal to 0.960 times 10 to the 9th millimeters to the 4th. Okay? Now, again, from a practical standpoint, what does this really mean? It means if I put a moment X on here, it's going to generate a moment Y. It's going to generate a moment Y because it wants to, you have coupling now between this X-axis and Y-axis. But the point of all this was just to talk about moments of inertia, sort of refamiliarize you or familiarize you with moments of inertia and what they are, and how to calculate them. Do we always have to calculate moments of inertia? No. No, we do not. A lot of times, we can look them up. Yay! Other times, we can get the computer to calculate them for us. So, again, preview of coming attractions. Here's geometric shapes of structural shapes. And sure enough, if I want to look at an I-beam over here, here's our little I-beam, and I want the moment of inertia of a specific I-beam that I'm going to buy off the shelf, and we'll look at this in more detail later. A W24 by 104 has a moment of inertia in the x-axis of 3,100 inches to the 4th. I don't have to calculate it. And it's symmetric, so I know it's going to be in the middle. Oh, and here's IYY, right, of 259. And you go, yeah, but I want to work in metric. Oh, okay, let's turn the page. And there's your metric values. You say, oh, but I don't want that. I want a C channel. Oh, well, here they are. C channels. Oh, no. What I really want is an angle. Well, guess what? Now you're going to get coupling, aren't you? Well, it even tells you where the principal axes are for that angle. Right? And then you may say to me, oh, but Mr. Wilt, I may not always have my book. I want to buy these things off the shelf, and I don't want to have to figure out what they all are. And I go, okay, let's get out our steel construction manual and look those up, shall we? What shape would you like? Let's see. We want properties of these shapes. So here's an I-beam, and there's the answers. Okay. So the good news is you don't always have to calculate these things. By the way, this book is all English. This book, right? Yes, it's a big book. This book is all English. I believe they make a metric version, but here in the United States, for good or bad, we're still in English units. Okay? Now, I hope that helps. If you say, gosh, I still don't get that, pretty much all I did was take you through the appendix in the book. If you still need more, read back through the appendix. I did the examples in the appendix. We'll do some more in class, find out some more moments of inertia, more centroids, but there's some help. There's other helps available in the resource section of our class presentation stuff. And if you still have issues, please give me a call. Let's see here. I want to bring up camera. How do I change the camera? I guess I can't. I don't know. Anyway, if you still have issues, here, select camera. It won't let me change. Anyway, if you still have issues, please give me a call, email, something. We can go through some more stuff. And again, there's other additional presentations that I put out there for you under resources. Okay, well, I've taken an hour and a little bit of your time. Thank you very much for listening, and I will see you in class.